All right, good morning. This is our ICCRG meeting. Let's wait another 2 minutes. For me, it's 9 o'clock. The clock there is 80:55. So let's wait a bit more. All right, more people are coming to the room. We can start. Okay. So welcome to the ICCRG meeting on IETF 126. I'm going to repeat some information you probably already know. This session is being recorded. This is an IRTF group meeting. So the IRTF follows the IETF intellectual property rights disclosure rules. Some information about that available in the RFCs on the slide. We also record audio and video from the sessions. If you have any objections or restrictions to that, or if you speak on the microphone or want to ask questions during the session, it means also that you consent to appear in the recorded material. Privacy and code of conduct. Routine, probably know about it. And most important, the goals of the RTF is that we conduct research. This is a place where we present work that is not ready yet or could be eventually forwarded to the IETF for standardization. Therefore, we don't develop standards here. Some more information for maybe new participants, how to choose your tool, the full or the Meet Echo Lite if you're participating remote. Some other resources on the agenda, Meet Echo information, and if you need some more assistance with technical issues. We are 3 in this group, so we rotate a bit. Riz is online, giving me support from the West Coast. VD is also somewhere, and sometimes I'm on site, sometimes I'm remote. So some people know me here well. The page and the mailing lists or the email from the ICCRG, you can reach us anytime you want. And as usual, we need a note taker. Who is going to do us this favor? Someone in the room could do note taking for us, please. Volunteers? No? Yeah, thank you very much. So we have a note taker already. On to the agenda. So we have quite a few items today, but also enough time to discuss if you want. First, we do the draft updates, and then we go to external speakers and other topics that we bring to the ICCRG because we think they are interesting and relevant for the community. So yeah, the next person to present. Oh yeah, sorry. So we have also an update on the active drafts here. So the LEDBET++ document entered the IFC publication queue. Thanks, Gori, for your review and emails that we have been postponing, but things are progressing here. And we have, as our first speaker as well, an update on the pacing. So yeah, let's move on to Michael's slide.
Good morning. If you know me, you know I can talk long and waste everybody's time, but not today. 2 slides giving an update. There were 2 versions of the draft since the last time this was presented. One is that now the draft discusses ABC, which I think is not really used by that name anymore, appropriate byte counting. This is there's an older version of the document that says also 5681, the TCP, Congestion Control RFC. It says that in slow start, you shouldn't increase by more than 1 SMSS for every ACK that you receive, so that if you lose a number of ACKs in a row, and then one will tell you you are now allowed to increase by 10, that would lead to a burst of traffic. And that is why that rule is in place. However, that makes less sense when you're pacing. And actually, HiStar++ specifies that this really shouldn't be done. And we document this. We say that HiStar++ recommends that, and probably it doesn't make that much sense to have that strict rule in place when you're pacing. Then there is some more FreeBSD text. There was an example that Michael, welcome, put into the document. And that was nice. It had a packet drill example, but then he made it even nicer. That's what this is. Just the example is clearer. It highlights the case a bit better. And then we made another update where VD finally got the okay internally to give us a bit more details about how Apple is implementing pacing. So the description now explains that there's an API that allows to enable pacing and set the maximum rate. So there's an application cap that is being applied, and then there's a burst. The way it's done is that there's a burst budget of approximately 244 microseconds. It's interesting that this is an approximate number of 240. And with a minimum of 1 MSS. This is kind of, it seems to me to be not very far from the Linux behavior where you have basically 1 millisecond, it's just a different number, but you're collecting for a certain time, and when you have enough of that, and then you exceed that time, then you send that out. So this is a creation of microbursts. Because I send timestamps using a leaky bucket scheme in that case, and these go further down in the system, just also as in the Linux way that is that we described, and then it goes to the AQM. So this is where it's being applied. And that is it. We did these few updates because these were things that we wanted to do. There was a request about the FreeBSD one, but no other requests from anyone about anything, I think. So, time to have more feedback and more inputs if anybody has anything, or otherwise we could maybe finish that document. That's it for me. Comments, questions?
Michael Jackson, this 244 microseconds number, I think Vidi said it comes from Linux.
She said it comes from Prague.
Oh, Prague. So I would be really interested where this number comes from, and if someone can give a statement where it comes from.
That was her answer to like Prague.
Maybe you were just, I don't know, random number.
It's a Prague number.
Yeah, there is an issue there. There's an issue with Prague, not so much with pacing as with burst, because Prague sets the threshold for starting ECN marking very low, and so it's fairly easy to exceed that threshold by sending a burst that's too large.
Ah,
And
okay.
so that's I have no idea what Apple did, but there is this actual issue in Prague and burst size. I mean, if you set your minimum burst to I think it's 2 milliseconds in Prague, you want if you set your queue, if you start marking the queue with a few milliseconds, obviously you don't want to send millisecond worth of burst because that's going to interfere.
That makes sense, yeah.
Now there is of course another issue is that if you want to have high performance with UDP-based application like Quake, you want to use general GSO.
Yes.
And for GSO to be efficient, you want to burst at least 10 packets.
Yes.
So there's a tension there.
Yes. all true.
Yeah.
So Michael Tuxen channeling Richard. He doesn't want to go to the mic. The number is 1/4096. He figured out.
Oh.
So.
And it's kind of a quarter of a millisecond, but just kind of in line with 2, power of 2. So great.
Yeah.
Cool. Maybe easier to implement with shifting or something. So. Yeah.
Yeah. So we probably do a working group last call in the mailing list and see what happens from there, given the silence. Yeah. All right. Thanks, Michael.
Thank you.
Let's move on to the next update, windowless cumulative SAC. It's there, Danyang?
Yes.
Yes.
Hello, Chair. Hello,
Yes.
everyone. This is Danyang from China Mobile, and my topic is windowless cumulative SHK extension for RDMA retransmission. And next slide, please. Good. Okay. We will no longer control this. Yes.
Slides are coming.
Okay, thank you.
Not there yet.
Oh, yeah. Maybe I can share my screen.
Reese has the controls. So
okay.
Let him share. Yes, now it's here.
Yes. Okay, the background is that large-scale cross-one data transfer scenarios have grown rapidly alongside the rollout of cross-regional computing infrastructure fueled by industrial digitization and cloud adoption. Cross-region cloud access and migration carry every large data volumes, creating strong demand for remote data migration. This draft proposes a windowless SACK method aiming to achieve efficient wide area transmission of large-scale data over wide area networks through RDMA. The problem is that how to increase throughput under the limited bandwidth conditions. So next slide, please. Also, with the development of new internet scenarios and technologies such as the high-definition video, cloud computing, big data, artificial intelligence, and the large models, users often need to transmit large amounts of data over a wide area. networks. At the same time, the wide area network environment is full of uncertainties. So the traditional RDMA method of go-back and packet loss retransmission is sensitive to package loss, and other retransmission methods rely on RTT and window size. Directly using the traditional packet loss retransmission methods cannot improve the effective throughput. So we want to enhance the good put is necessary to improve the current ASIC mode. So next slide, please. Oh, so next slide. Oh, yes, thank you. So we propose the dual-dimensional packet loss retransmission mechanisms for timing and counting based on the network environment and the size of the few packets to be sent. The sending rate is precise, and the cumulative confirmation time and T and the cumulative received data packet number N are also determined. So then the window limit is removed. The sender doesn't need to adjust the sending rate according to the packet loss situation. It only needs to continuously send data package message at the precise rate, and the receiver continuously receives data packet messages within the range of cumulative confirmation time T and cumulative received data packet number N, and arranges them in the receiving buffer according to the package sequence number. And after reaching the precise time T or the cumulative received data packet number N, the receiver triggers the confirmation mechanisms and feeds back to the received data packet sequence numbers through the ACK message to the sender. So subsequently, the sender checks based on the received ACK message whether there are lost data packets. If there are lost packets, it resends the lost packets data packets to the receiver. So next slide, please. In order to achieve the ACK mode, we make a new ACK message format, and is add a TCATH to the standard RDMA message format, and is the example of the TCATH message format. It contains the segment name, last finished PSN, and segment one left and one right, segment two left and two right. So next slide, please. So in this page, we introduce the meaning of the of each part and the rules for the receiver to determine whether to resend the data packets are as follows. Segment to left, to right, and so on. Retransmit the data packet number within the range of the segment one left plus the last finished PSN, and to the segment one left, and the segment one right to the segment two left, segment one right, and so on. If segment num equals to 1 and the last finished PS equals to the segment 1 right and equals to the maximum number of the sent data packets, it means that there are no retransmission is required. And if the segment num equals to 1 and the last finished PSN equals to the segment 1 right, but this is less than the maximum number of the sent data packets, it indicates that a tail package loss has occurred. Therefore, data packets numbered from the segment 1 right plus 1 to the maximum number needs to be retransmitted. So this is the whole process of our draft. Thanks. And any questions?
No questions in the room, in the chat. No.
No, okay, thank you.
No. So let's move on to the next presentation, testing congestion control. Oh, wait, controllers.
Good morning. I'm Mohit from NITK Surathkal in India. This is to give a quick update on the hackathon. I did make the same presentation in CCWG yesterday. So if you are there, you might want to consider finishing some emails because I'm going to repeat the same thing. But of course, with the focus of ICCRG, as you see this hackathon, typically we try to do it with the topics that are aligned with CCWG, ICCRG, also TCPM and TSVWG. We had initially 5 objectives, but we reduced it to 3 considering the time that we had in the hackathon. This time it was a relatively shorter hackathon than every year, every IETF that we have. So we had 3 objectives. The first 2 are actually aligned to TSVWG. They are on queuing. The third one is related to the Pico Quick, which is a quick integration that we have done with NS3. And then I have some more points to discuss that are pretty relevant to ICCRG and the internet drafts and the RFCs that have been produced at ICCRG. The first objective talks about the comparison between FQ Codal, which is RFC 8290, and FQ Pi, which is our internet draft in TSVWG at this point. And we did the comparison of both of these algorithms using a Samsung phone, configuring these algorithms as the mobile hotspot, and also in a Wi-Fi AP provided to us by Quantum Networks. So thanks to Samsung and Quantum Networks for giving us the devices. This was the setup. So we had a client. This is my student's client, Abhyuday, who is on site with me. And then there's another student, Vishal, who participated remotely from India. So this is his laptop, which was connected to the mobile device, connected to the access point, and then we were using the buffer bloat server. I'll not spend more time on this. As I mentioned, this is more relevant to TSVWG, but if you are interested, the slides are up. The internet draft is in TSVWG. If you have some points to discuss, I'll be here throughout the IETF. We'll be happy to discuss these points. This was the setup that we had for the access point. Pretty much similar, just that instead of connecting to the mobile hotspot, we were connecting to the Wi-Fi AP. Again, we had results done for this. For running these experiments, we used Flexible Network Tester, which is kind of a Python wrapper on top of IPerf and other networking tools. It has implemented some specifications like RRUL, which is real-time response under load. So it pumps in bidirectional traffic and then uses ICMP packets to see whether RTT is acceptable or not. It also has several other tests. We chose some of the tests to run during this experiments. I'll go to the next slide with just an observation that has stood out from last 4 IETF hackathons that we have done is something that tail latency in FQPi we see to be better than FQ Codal. We are still running more experiments. We have done more experiments on NS3, but these were the experiments on Wi-Fi. The ones that we did on NS3 were not using Wi-Fi. So in all different setups that we have seen, we see a clear improvement in the tail latency. But yes, the work is still going on and more experiments are to be performed. Talking about now something related to congestion control, which is also relevant to CCWG and ICCRG, is Pico Quick. So in past few IETFs, we noticed that Pico Quick is something that a lot of people were using at IETF for different kind of work. And also we saw recently, according to the stats from last 5 years, that more than 1,500 papers have been published using NS3. But NS3 does not have a native model of Quick. On the contrary, we have several other user space implementations of Quick that are available. So we decided not to build a native model in NS3, but rather to use something that IETF is already using and integrate it directly with NS3. So PicoQuick is a C implementation of Quick and Multipath Quick. Christian manages it very actively, follows RFC 9000, 9001, 9002. And on the other side, NS3 is something that provides you reproducibility, scalability. So we have now integrated it. This is a sample result. If you are interested to look at the code, here is the QR. You can scan it and you can look at the code. It's a very thin wrapper that we have built to integrate both the libraries in such a way that if one goes on to get updated, it will not impact the integration as such. So you can actively keep working on PicoQuick and keep adding your algorithms or your features. You can also continue to work on NS3 in parallel, and you wouldn't need to touch this wrapper again unless there are significant changes in the public APIs that PicoQuick exposes. We have also provided around 5 to 6 examples for the users to get started with. One example is competing congestion control. So Christian has an internet draft in CCWG, which is called a C4. So you can see one experiment that we have run has a flow with C4. There is another experiment that runs cubic. You can use BBR. You can use other congestion control that PicoQuick supports. And you can use these several topology helpers that are available in NS3 to quickly spin off a topology and then run these experiments using PicoQuick. So these are the works done. And we have also provided one example for multipath quick. NS3 did not have any example of multipath, not even multipath TCP. So this is the first multipath example that now NS3 will support. So please feel free to use it and do let us know whether you find any issues or if there are certain things that we missed out. Something that we did not do at the hackathon, but we did between the last IETF and this IETF. The first bullet is related to the work happening in TCP/M on PRR. So now we know PRR is a standard in 9937. The earlier one was an experimental RFC 6937. And we found a small bit of alignment that was supposed to be done in FreeBSD. So a couple of my students worked on this project and we pushed the patch to FreeBSD. And on Saturday, I met Richard and Michael, and thanks to them, now that patch is merged. So this was the first contribution from our institution to FreeBSD, and we look forward to having more active participation. The next bullet talks about 2 things that are directly relevant to ICCRG. LEDBAT++, I saw Simon's slides. I think now it's in the editor queue. But our LEDBAT is already RFC 9840. There was no implementation of these 2 algorithms in NS3. So our team of students have implemented LEDBAT++ and R LEDBAT, and these are the links to the merge request on the GitLab repository of NS3. LEDBAT++ has been already reviewed by the NS3 community. I am a maintainer for TCP and queue management in NS3. But then there are other NS3 maintainers who have actively looked at LEDBAT++ and given some very good feedback, and it's on the verge of getting merged now. But we haven't yet received much feedback on our LEDBAT. So I would encourage community members, if you are working on any of these algorithms and you plan to test them or use them, it would be great to have your feedback on this implementation. For example, prior to implementing LEDBAT++ and R LEDBAT, LEDBAT was already available in NS3, but when we worked on LEDBAT++ implementation to get started, we identified there was a bug in the LEDBAT implementation of NS3. So that was a pretty serious bug, and that went on to get fixed now. So we had to fix that and then implement these algorithms. So more people looking at it will definitely help us to ensure that we have lesser bugs in these implementations. Apart from that, like you saw, I mentioned in my previous slide that we used Flend to run the test. So what we noticed is a lot of congestion control algorithms and queue management algorithms are supported in NS3, but we don't have an application like Flend that people could directly use. So we have built now, as a part of the Google Summer of Code project, the student who is working with me in this year, we have built a Flend-like application for NS3. So if you had an R-rule test that you were running on a Flend on a live test bed, you could use the same R-rule test now in NS3, and it will give you a similar type of results in the same format, same candle plots, same cumulative distribution function plots. So we have tried doing this implementation in a way that you don't see the difference whether you are running on NS3 or you are running on a live test bed. The code is here. This project is still going on. The student is going to submit the final code by the end of this month, and it will be then available on the GSOC website for review. So please take a look at it and let us know if you have any other observations that we should improve on. And finally, we have added some new topology helpers in our tool that we have built at NITK. We call it as Network Stack Tester. It is a Python wrapper on top of the Linux network namespaces that allows you to quickly spin off topologies. The most important topology helpers that we have added are for multiple bottleneck topologies. So dumbbell topology is very well known and used for congestion control, but we noticed that now there is a lot of interest in multiple bottlenecks also in the network. So we identified a couple of papers from 1980s called Generic Fairness Configuration 1 and Generic Fairness Configuration 2. These are two very well-known topologies for evaluating congestion control on multiple bottlenecks. Now we have these two helpers readily available in Nest. You can quickly spin off a multiple bottleneck topology without having to spend time. And those are already merged in Nest. Here is the code and some examples for that. So that's all from my side. What I wanted to mention is that we will continue to build more features and more algorithms in NS3 or Nest. What we seek inputs from ICCRG is to let us know whether if there is any protocol of interest to ICCRG, or if there is any feature that somebody would like to see, so that we can allow more internet drafts to be evaluated in the process as they become RFC. Thank you. That's it from my side.
Questions from the room? I mean, we have been in touch with you, especially Reese, about having the a similar a similar evaluation suite that you have for AQM, but for congestion control.
Oh yes, we have. So I did not mention about the. So we are building a congestion control evaluation suite, which is in compliance with RFC 9743. We have made very good progress on that, but that still is work in progress. So maybe in the next.
It would be nice to hear about it.
Sure.
Yeah.
Okay. Thank you. All right.
Thanks, Mohit. So our next speaker.
Thanks, Chair, and thanks everyone. Good morning, and apologies for not being with you on site. The presentation is based on Lickli's law for queuing theoretic approach for congestion window update. The easy part here is that this is about congestion window update. We have additive increase, multiplicative decrease, and here and cubic increase. Here we are looking at queuing theory to determine the congestion window update. The paper or the presentation is based on a paper that has been published in Electronics, MDPI, and another paper that will be published soon, and I can share that once it's published with everyone in the mail list. Let me see. Okay, so this is sort of the problem we're trying to address, which is a common problem that we always address when we do congestion control algorithms. It's about throughput delay efficiency, especially to ensure that we can maximize the power metric. We have on one hand high utilization, high delay regimes. On the other hand, we have got the low delay underutilization regimes. We want something that's balanced so that we can improve the power metric. Okay. Just a comparison of the different approaches. The first one is around loss-based, which exhibit high standing queues and loss cycles. We have got delay-based, which tend to underutilize the bandwidth. And then we have got BBR, which is a model-based, and it tries to implement clear optimality to ensure that the in-flight data is equivalent to the base bandwidth. What we are trying to do is also to achieve the same, but by regulating RTT using queuing theory. That requires a suitable RTT target, which probably is the biggest problem, but that's something that can be solved separately. Queuing is based on the way the sender or the end user looks at the network. The sender looks at the network as a big pipe or a queue. So we're looking here at the network as a queue, and we model it using Lickli's law. Yes, indeed, there could be argument to say, the network has got the topology can be very complex, but from the sender's point of view, the sender simply sees one pipe, and that's what we are using. That pipe can be stochastic, and in this presentation, obviously, we do assume static, not because we can't also do computation when the pipe is assumed to be stochastic. In that way, then we use Lickli's law, which says that the occupancy is equals to arrival rate times delay or propagation delay. Typically, Lickli's law work on averages, but of course, it assumes a certain amount of time, running time, to average, and that running time could be milliseconds, could be microseconds. As long as you can do those measurements and it's reasonable in the environment, you then can be able to apply Lickli's law. But also if it's possible to differentiate the occupancy, to differentiate the delay, which is R here, then we can create a differential relationship of Lickli's law. And in this case, that's what we are doing. And we are assuming that if the delay does not change and the delay remains constant, then we can have a condition. We refer to this condition as stationary delay. And that condition says that the change in occupancy with respect to arrival rate should be equal to the delay. Obviously, as we move towards high utilization, the delay becomes so high, and we attempt to keep the delay at some level that is specified. And in that way, we define an R target, which is defined by alpha times the propagation delay, or in this case, propagation round trip time. So under this adopted single bottleneck, the condition then motivates us to operate near the base bandwidth delay product, which is Glenrock optimality. And it also allows favorable throughput delay trade-off. Based on the condition, the stationary delay condition, we are able to develop or design a predictor step and a corrector step. A predictor step is trying to estimate the deviation from equilibrium or the target RTT, the target RTT. So the predictor step is trying to calculate that deviation, and the corrector step is trying to find a congestion window that will counteract that deviation. So we first measure congestion window W, in-flight data L, or occupancy L, and as well as delay or round trip time delay, which is R. And then we predict the in-flight data that we would like to have in order to ensure that there's no deviation, and we correct using a congestion window, and we use that in a cycle. Obviously, to do this, we also, while the purpose is really to see how we can use these relationships to do congestion control. There are practical issues in the implementation. The first practical issue is around minimum RTT tracking. Currently, we are using periodic probing that is similar to BBR. So we are able to update minimum RTT whenever RTT is lower, but also to detect minimum RTT when it's increasing. Also, you have to make sure that there's fairness and coexistence, because any congestion control algorithm that doesn't have fairness, then it's no point even to start. There's no viability with that. So again, the RTT probing does help in terms of fairness, but it also reduces bias for stale minimum RTT, and in that way, it improves fairness. We also use low start, like in new Reno or other cubic, to start with new start. Slow start before we get to congestion avoidance. In this case, when we are at congestion convergence, we then use QT SDR, which is we are denoting the algorithm that we are developing, which stands for queuing theoretic stationary delay regulator. The default alpha for our RTT target is 1.2, which we have determined empirically to be more or less stable, but also low enough, which is about 20% of minimum RTT. Then in terms of the simulation, the first, we have basically done a singly Brooklyn-Eck, a simply topology, and we are assuming 100 megabits per second, one-way Brooklyn delay of 20 milliseconds, which translates to base round-trip time of 40 milliseconds. We ensure that the buffer size is large, just so that we can see that we can regulate the target RTT. So the first is about regulating or optimizing the in-flight data so that it's close to the base bandwidth delay product. And in this case, you can see QT SDR is very close to it. BBR normally is a little bit higher. It's always about 2 times the base BDP. Obviously, that's a design issue. Then loss-based algorithms are quite high in terms of in-flight data, and they depend on the buffer or the buffer size. This is the distribution as far as the RTT. As you can see, we are first able to reduce the RTT so that it's close to 40 milliseconds, which is the base RTT. And also the oscillation is low, which we can see around the interquartile range shown by the box plot. The next one is the power metric, and this is normalized power metric. And what you see is that the QT SDR is quite high, close to 0.8 in terms of the power metric, compared to cubic and new Reno, which are quite low, around 0.2, and BBR around 0.5. Then in terms of the buffer size, the effect of the buffer size, there's no effect in QT-SDR, there's no effect on BBR. Then on cubic, the higher the buffer size, the lower the power metric. So again, we are able to ensure that the algorithm operates independent of the buffer size. Then in terms of fairness, maybe before I touch on fairness, a slide that I didn't put here talks to good put or throughput. What we find that QT-SDR is comparable to all the other algorithms. So the fact that it manages or it regulates RTT, it does not then make it deteriorate the throughput. And then in terms of fairness, again, the fairness is comparable. All of it is above 0.9, which is reasonable fairness. Again, what we are saying is that the algorithm does not deteriorate fairness. Of course, this is a fairness of the same type of algorithm. We haven't done fairness in heterogeneous configuration. So in conclusion, one queuing theory provides a practical RTT regulation principle, and we have shown that stationary condition can be translated into send-aside predictor corrector congestion window update. We have also evaluated the QT-SDR, and we show that it remains close to base BDP, substantially reduces RTT and achieves higher normalized power. And then the results, it shows that when we can almost complement loss response and bandwidth probing, then the next step is looking at adaptive target selection of the alpha or the target RTT, so that you can regulate it dynamically. And then last point that I want to add then is that we don't see this to necessarily becoming a standalone and probably mainstream congestion control, but we see the concepts that can be used with other congestion control algorithms or even motivate future approaches in terms of congestion control. Thank you so much.
Go ahead. Is it turned off? Can you use this, the one in the front?
Thanks for the presentation. I'm Roland. One thing is that typically it's not that trade-off that you showed in the beginning. So you can have low delay and high throughput actually. So that's just one comment. So it's not mutually exclusive. The other thing is, I'm not sure how, queuing theory is nice, but actually the systems that we are using are in this rho equals 1 regime, which means typically then you cannot apply queuing theory quite well. But it seems to work somehow. So my concern is, did you test this with, let's say, loss-based congestion control at the same time? So typically what we see is that delay-based congestion control gets suppressed by loss-based congestion control flows. And the other thing is delay-based congestion control typically has problems with varying, let's say, delay due to access media, for example. So did you test something on Wi-Fi?
Yes, no, thanks. Let me just quickly start with the loss. Yeah, the coexistence of loss-based with that has not been tested. However, let me just give the belief. The belief is that what will happen is that it will then also start increasing the base RTT, which based on the increase with loss-based. Obviously, that could potentially cause a bit of instability, but I think that's just a shortcoming of the approach. Yeah, so we haven't tested it, and the belief is that because of the ability to detect the increase in RTT, it will increase with loss-based RTT. Of course, that is not desirable. Then on the delay-based congestion control, this, if I suppose it has the same sort of problem that you'll typically have in most delay-based congestion control. However, we have tried to mitigate that by ensuring that we can quickly detect when RTT increases, and as I explained with the loss-based algorithm. The main purpose right now is really to show the mathematics that it can work. Again, the mathematics, as you rightly say so, it depends on Lickli's law applying, and yeah, the conditions to ensure that Lickli's law can apply. That is the environment is close to endogenous as opposed to exogenous.
Okay, so my main point was you should test it with let's say artificial jitter or natural jitter that is caused in the system. So that could the variability in the delay measurements could actually be challenging for your algorithm.
Yeah. No, thanks. Yeah, that's true. I agree with you there. Yeah. Maybe I can just add to say that I will put this on GitHub, and probably if that is the implementation on NS3, I'll put it on GitHub for anyone who would like to test it. And yeah, I don't know if it's possible, Simeon, to put it also on Data Tracker.
On the Data Tracker. Yeah.
Okay.
We don't have more questions in the room, so let's move on to the next speaker. Thanks, Dumisa.
Thank you.
So, hello, Mingqing. We can see the slides. We can see you.
Yeah. Yes, I can. Can you hear me?
Yeah. Thanks
Okay.
for accepting our invitation to come by and talk about mooncake. So you can take it away.
Yeah, thank you. It's my honor to share our progress on disaggregated large language model inference in this IETF conference or workshop. Today I will mainly talk about our recent progress on how we improve the transfer engine which is a core component and of the mooncake system. Also, we will talking about some background such as the new agentic workload and why it is important. So you know that currently the large language models are some pictures are missing here, but essentially, currently the applications of large language models have changed from the original chatbot, which typically we have only a single turn response, to agentic workload, which means that you will use a harness that will driving multi-turn and very complex execution topologies, which also means that it will take a lot of tokens. It will consume a lot of tokens per request, which also leads to the increasing of the consuming of the inference cost, which as a result, the current GPU are mostly used in the inferencing the models rather than the training the models. But originally, we only built in the so-called compute infrastructures, which is typically measured by how many computation power, such as the P-flops, how many petaflops that these computing infrastructures can hold. But nowadays, we want to build not only the compute infrastructures, we want to build the token factories. And a token factories should be measured by how many tokens that it can consume, how many tokens it can produce per second. And there is a very huge gap between the computation power measured by petaflops and the token processing capability measured by token per second, and the difference or the gap is determined by your inference infrastructures, and that is the reason why we need to build, such as the title of this slide, the disaggregated inference architecture, to improve the capability of transforming the computation power to the token processing power, and that is the main topic of today. And of course, that as you can see that in our traditional computer architecture, we will build some kind of hierarchical of memory. That which means that we will have also a very expensive, very small capacity, but very fast the cache, and we will combine it with the slow but more cheap SSD or DRAM. We will combine a hierarchical of DRAM in order to balance the cost and the bandwidth that we can achieve. Similarly, in the intelligence or in the nowadays large language model processing, we can also have different kind of heterogeneous accelerators, such as we have high-end GPUs which equipped with high bandwidth memory, which is expensive and small. And we also have middle layer GPU accelerators, which is equipped with GDDR, which have a slower bandwidth, but maybe less expensive. And we also have DRAM, which is the cheapest in terms of the capacity per dollar. So if we can combine all these different kind of heterogeneous accelerators, we may be able to have a better TCO of our super accelerators. And this is the reason why we will, this is a more detailed explanation. For example, I'm from China, and in China, we have several different kinds of accelerators, such as the H800, which is a flagship accelerator. So it is typically good at T flops per dollar. So it is computation power is good. And also we have H20, which is the limited which computation power is cut because of the limitation of experts, whatever, but it is also more cheaper. So it is good at the bandwidth per dollar. And also, of course, we have the CPUs equipped with DDR5, which will have, which will be good at the capacity per dollar. So if we can disaggregate the LLM inference into 3 stages, 1 stage consuming computation, 1 stage consuming bandwidth, and the 3rd stage consuming capacity. We can use different kind of accelerators for different stage, and that is the main idea of our mooncake system. So essentially, this mooncake system is it is based on the internal characteristic of the large language model inferences. As you can see that it can be partitioned into 2 stages. The first stage is called the prefill, which will consume all the input tokens simultaneously. It will process them concurrently, so it consumes the computation power at most. And in the second decode phase, it will decode 1 token per iteration. So for every iteration, it will scan all the weights of your large language models, which is very huge. So in the decode phase, it will consume the bandwidth at most. So now we have 2 stages, 1 consuming computation and the other consuming the bandwidth. And how we connect these 2 stages? Actually, we connect them by transferring one key matrix called KV cache from the previous stage to the decode stage. And this KV cache, it is called cache because it can be cached and reused in the second round. So as you can see, if you have 2 different questions, one question is, what day is it today? And the second question is, what day is it tomorrow? As you can see, the first 4 tokens are the same in these 2 questions. So we can preserve the original KV cache, process the output result of the first question, and reuse the KV cache for the first 4 tokens in the second round. So it is in order with this reusing, we can reduce the computation by storing and reusing the KV cache. So this storing and the reusing, which means that the caching of the KV cache require capacity at most. So now we have 3 stages. 1 computation, 1 bitewise, and the third is for capacity. And we can, as we have mentioned before, we can use H800, good for computation for prefill. Use H20, good for bandwidth for decode, and use DDR5, good for capacity for catching all the reusable KV cache. And that is the main idea of our disaggregated architecture of large language model inference, which is called mooncake. And this mooncake system is originally currently the inference platform of the Kimi, which is known, or in the last year, it is known for its open source model K2. And in the just 2 weeks before, it is also used for serving the current most sought out open weight large language models, Kimi K3. And we will open source Kimi K3 in the open weight Kimi K3 in the next week. So it has experienced very high bandwidth and very high concurrent user usage. And its main benefit is that we increase the throughput of Kimi by as large as 75%, which is by using this disaggregated architectures. As you can see in the right side of this slide, we have standalone prefill instances, which is consumed by computation intensive GPUs such as H800. And we also have a standalone decode pool of GPUs, which is consisted by bandwidth intensive accelerators such as H20. And in the middle, we have the KV cache pool, which is pulling all the DRAM and the RDMA bandwidth of all these GPU servers. So we have 3 different components. And more importantly, because currently the large language models are all sparse MOE models. So in different prefill and in decode, typically we will use different parallelism strategy. For example, in the prefill, we may use tensor parallelism, and in decode, we use expert parallelism. So this different parallelization also require that you need to disaggregate the prefill pools and the decode pools. And in order to connect all these different components, you need to make best use of your GPUs, and that is what we have open sourced the mooncake. The mooncake open source library, which is used for. And the second goals of this mooncake open source project is that we have contain all the reusable KV cache in this very large capacity KV cache pool. Because currently, if you have a lot of concurrent users, the KV cache per user may be several megabytes. And when it multiplied by the maximum number of users that you want to serve, the result aggregated size of the KV cache size can be hundreds of terabytes or even petabytes. So this is a very huge size of the KV cache. And with all this, these are the original usage of the mooncake, which is used for catching the KV cache and also transferring from the prefill to the decode side. But from 3 years ago, the mooncake system has developed in many more usages. Currently, we are not only disaggregating the large language model inference to only 3 stages. We are actually, as you can see in this slide, we have disaggregated into 5 or even 6 or even 7 multiple different components, such as, for example, currently the large language models not only congest text materials. It can also congest images and the videos, which is processed by a standalone component called a vision encoder. So we can disaggregate these vision encoders to some more GPUs, and this leads to another disaggregation architecture called EPD, which originally is prefill and decode, PD disaggregation. Now we have vision, prefill, decode, disaggregation, so 3 components. And also, originally, we only use disaggregation in a single data center, but now we have proposed an architecture called prefill as a service, which means that you can keep the prefill GPU on one data center and the decode GPU on another data center, and connect them via some different kind of via the wide area network, and that is possible. So we have evolved the mooncake system into different components. Once you want disaggregation, you can use mooncake to connect different components, and that is the main goals of why we developed the mooncake system. And also the mooncake system has been open sourced and used in many companies, such as not only the Moonshot AI, but also Alibaba Volcano Engine in approaching AI and finance, and also NVIDIA and many internet components, and it is also integrated in most of the open source inference engines, such as VLM, SGRON, and NVIDIA's Dynamo system. So it is one of the most standard middleware for the current large language model inferences. And the main objections, as you can see, we want to transfer the key cache or other materials as fast as possible, and we want to store more key cache in order to reuse them as much as possible. And we also want to keep it easy to use, so that you can use it in the more and more scenarios. And that is the main objections of mooncake. So we can, because of the time, I want to directly go to some our recent advance of the current mooncake. So as you can see, that this is the original experiment result of how we use mooncake. The x-axis is time between tokens, which means that how many tokens can be produced per request, and the y-axis is the capacity, throughput capacity. As you can see, at the lower time between token you want, or in another term, the larger the tokens per request you want. For example, if you only want 10 tokens per second per request, you do not need the disaggregated architecture. But if you want 50 tokens per request, you need to disaggregate the prefill from the decode in order to have a better throughput. And that is the main reason why we use mooncake. But now, this is the original case, but now we found that the current network is evolved into a very more and more complex, which means that we can have many heterogeneous network interconnects. For example, we have GPU direct RDMA for scaling out network. We have NVLink in the scaling up network, and also we have TCP for the cross data center network. But in the original, this is to a so-called multi-pass selection problem. But in the original design of the mooncake, we need the users to imperative to select which protocol you use before you using the mooncake transfer engine. And that is not good for this kind of heterogeneous network processing. As you can see, that originally we ask users to imperatively select which kind of network protocol you need at the startup time, and this is statically binding. And then we will have a fixed and the state blend path selection and scheduling policy, which will lead to very large P99 latency because of the congestion of your network. And also, if some of the network interface card is failed during the transferring, you need to recover the network transferring manually, and that is not good if your clusters, the size of your cluster is very large. So in order to resolve all these challenges, currently we have developed a new technology called transferring engine new technology. And the main objections of this new technology is to resolve all these three problems. The first is when we have originally we select to use GPU direct RDMA and it is failed. We want to use some kind of relay in order to recover from this kind of stack banding. And we also want to recover from the congestion, which means that we want to rebalance the network in order to pull in all the network interface card in order to make best use of the aggregated bandwidth. And also we want to automatically recover from a partial failure of only one network interface card, because currently for every GPU servers it will have multiple network interface card. So if only one network interface card is down, we can still use other network interface card to recover the connection as long as we can relay it, for example, via the NVLink. So with all these three objections, we have developed the network transfer engine new technology. And its main objections and abstractions is that we use a unified segment abstractions to unify all different kind of network topologies. As you can see, because that essentially all the large language model inference workloads are essentially moving some byte buffers from some locations to some other locations. So we can abstract away all the different kind of protocols by using this memory layout. We just provide the size, the pointers, the offset of some byte buffers, which is the source byte buffers, and also give the destination byte buffers. And we just declaratively is saying that this is my network transferring intentions, and it is the responsibility of the mooncake transfer engines to choose automatically which network protocol we use, which route we use, and that can be all handled automatically. And it can be NVLink, it can be RDMA, it can be TCP, and it can be even TCP over wide area network. And the material can be DRAM, can be HBM, and it can also be SSD and HDD, because we can also abstract SSD by byte buffers, and they can be all the different kind of implementations can be all abstracted away via these unified abstractions. And then we can choose different, but even without the different implementations, we still need some kind of locality affinity. So we need to automatically finding out what is current topology of the network in order to help the system to choosing the locality affinity. Try best to do not cross data center, do not cross PCIe switch, and do not cross the NUMA selection. So that this is automatically found and used in the dynamic route selections. And then we can also install different kind of protocols by even with the same abstractions. And then even if, for example, we currently have RDMA available, NVLink available, and the TCP available, So in the first choice, we will choose RDMA, and if the RDMA is not usable, we can use NVLink as a relay to find other RDMA route. And if both the RDMA and the NVLink is not usable, we can still fall back to the TCP link in order to make our transfer link as high available as possible. And that is very critical in the real world large language model transferring. And because of this kind of heterogeneous network, we need some kind of spreading of the network package in order to achieve the best latency. And this is what we call it the adaptive slice spreading mechanism. Essentially, it is very similar to the network spreading of the traditional TCP packages. We just have some kind of latency estimation, including by measuring the network infrared bytes, the slice length, the penalty factors, and the bandwidth, the current usage of the bandwidth. And we use all these metrics in order to achieve a very the fairness of the network. We choose between the network interface card, which is the most low, which network interface card can currently have the lowest latency, the lowest bandwidth usages. We choose this route in order to have a better aggregated bandwidth. And also with all this aggregated bandwidth and aggregated pooling of the multiple network interface card, we can also assure the resilience and the self-healing in order to achieve the net resilience, which, as you can see, just the link level resilience. If one network interface card is failed, we just find the other network interface card that we can still use to connect with each other. And even if the RDMA is fully down, we can fall back to the TCP cases. And finally, we can currently present some evaluation of this network interface mooncake transfer engine new technology by comparing with our original implementation, the mooncake transfer engine, and the NVIDIA's implementation, the NVIDIA Nexus. And as you can see that essentially, because we can dynamically choosing the best network interface card, when we are transferring a large chunk of data, it can have a better throughput or a lower latency. The reason why the larger chunk we have, a larger throughput gain we can have, is because that when we transfer in this large chunk, originally in the original implementation, it is statically partitioned to 64 kilobytes and evenly spread to multiple network interface card. And it is typical some of the network card will be slower than the others. So this struggle will lead to the average throughput lower than the expected bandwidth. And by dynamically selecting the network interface card, we can have better usage of the bandwidth. And also, we make use of this better bandwidth in many real-world usage, such as, for example, we use it in the reinforcement learning. In reinforcement learning, one important case is that after the training, you need to update the newest version of your model weights to order serving inference in order to roll out, and this needs to transfer in the whole weight of your model. And currently, the size of the model is larger and larger. So this trunk is very large, and the transfer engine new technology is better in this case. And also, we have also used in the KV cache reuse scenario, where the larger size or the longer context you have, the better benefit that is the transfer engine UT will bring you. And finally, as you can see that all our technologies have been open sourced in this URL. You can find this organization in the GitHub, and this Mooncake is the host repo host all the source code and the evaluation reports that we have just presented. So if you are interested, you can come to the GitHub, and we can, if you are interested, we can also collaborate on this open source project. So that's my presentations, and I'm happy to take any questions.
Thanks, Mingxing. Any questions from the room? No. So one of the motivations that we invited you here is also because we use Mooncake quite extensively at Red Hat to look how LLMs work as workloads, as applications, as we develop the platform and also integrate the software with these different accelerators. We had, at the beginning of this exercise, very little idea how all these operations in LLMs, from PD disaggregation, KV cache exchanges, very little idea how these things behave on the wire, and whether we are using any libraries provided by NVIDIA that integrate very tightly with their hardware and run over RDMA, or we use like an engine for distributed inference such as LLMD, which is something that Red Hat is behind, to be agnostic to the transport, whether it's RDMA or TCP that is underneath. So we have been working with TCP zero copy to see how far we are in terms of performance to RDMA. So zero copy is something that, if I'm not mistaken, Google upstreamed not a very long time ago. We backported, we work a little bit on that. So the main motivation here was to have Mooncake as is basically a trace basis application that you can use to understand how LLM as an application behaves on the wire and how the network can or cannot absorb all these operations that these models do. So thanks very much for coming by and showing your work. Your paper and your open source stuff is very useful for us at Red Hat as well.
Thank you.
So let's move on to our last talk of the day. Ayush, so.
Okay, so my goal for today is to try to convince as many of you as possible that maybe bandwidth fairness is not the right goal for the networks that you're running. And I'm going to try to make this argument by presenting this paper that we presented at NSTI earlier this year, where instead we said that what we call approximate performance isolation is a better goal for your networks. So if you run a network, the congestion control algorithms that run within your network are going to be very important. And if there's any place where this is not going to be a hard sell, it's probably ICCRG. And this is not just because of the reasons of performance, but this is also because it's consequential in terms of how you size your buffers, what AQMs you deploy, and in the context of the internet, especially, how you think about fairness and the deployability of these congestion control algorithms themselves. So this last concern here, which is regarding fairness and deployability, this has gained particular attention in the recent years, especially in the internet context. And a lot of this is driven by the fact that today the internet hosts a heterogeneous mix of congestion control algorithms, often a mix of algorithms that have been found not to play very fairly with each other. So for example, two of the most popular congestion control algorithms on the internet are Cubic and BBR. And there's been vast amounts of work that has revealed that these two algorithms don't play fairly with each other when they interact with each other in certain network conditions. So just to quote one of these measurement studies for 2019, they observed that a single BBR flow was consuming a fixed 35 to 40% share of the bottleneck bandwidth, while sharing the same link with as many as 16 cubic flows. Now, of course, given the significant unfairness results that have been found in control tests, there has been a lot of discussion on how we can make these congestion control algorithms more fair, how we can review the deployability standards on the internet, and so on and so forth. These discussions have happened both at SICOM as well as ICCRG and CCWG here at IETF. Now, what I find particularly interesting about this development is that we've been doing congestion control on the internet for decades, yet this heterogeneity-driven unfairness on the internet seems to be pretty recent. And I sort of wanted to delve a little deeper into this question to sort of understand where this unfairness is really stemming from on the internet. So to answer this question, what we did was about in 2024, we built a measurement tool that could measure what congestion control algorithm a website is using, as well as over live sessions, figure out if the video stream is using a different congestion control algorithm compared to your ad loads or something else that the website might be doing. And some of the key results that we found out was that different websites deploy different congestion control algorithms, but more interestingly, these algorithms can differ across regions. So different regions, the same website can deploy different algorithms in different regions. And even within a website within the same region, depending on the content that you're delivering, you could deploy a different congestion control algorithm. So for example, over here on twitch.com, we saw that the video was being delivered using BBR, while the static assets and the banner ads were being delivered using Cubic. So this really makes things very interesting, and this really points out that the heterogeneity on the internet is really driven by the fact that a lot of people are trying to do a lot of different things on the internet. More specifically, I think what this development brings into question is this notion of bandwidth fairness that we have been pushing on the internet for many decades now. And the reason I want to review this question is because bandwidth fairness is a great goal for the internet if two things are true. The first is that your bandwidth must be finite, and this does make sense in the internet context, and it makes sense to come up with a good way to share bandwidth. But the second stronger assumption that bandwidth fairness comes with is that everyone only cares about throughput. Now, given these measurement results, the second assumption is sort of weaker today on the internet, because if everyone did just care about throughput, they would all be deploying the same congestion control algorithm that optimizes for just throughput. And the reason this doesn't happen sort of falls in line with the observations that I made earlier, which is that because different people deliver different things on the internet, they want to make different trade-offs, and therefore they choose different congestion control algorithms. Now, this is not a new result. This is something that we know really well, right? So for example, two congestion control algorithms in the Linux kernel, let's pick Cubic and Vegas, for example, we can see that they use the same network very differently. So for example, over here, Cubic, which is a well-known buffer filler, it's going to fill the buffer with packets in order to maximize throughput, whereas Vegas is going to be a lot more conservative, give up a little bit of throughput, but minimize delay. Now, the problem and the unfairness happens when we try to mix these competing goals together. So if I take the same two algorithms that are performing reasonably well here in this isolated setting, and I put them together, we see that now Cubic steals most of the bandwidth, and Vegas starves for any bandwidth necessary. In particular, what I would draw your attention to over here is that in this two-dimensional figure of throughput versus delay, what's essentially happening when these competing objectives compete with each other in the network is that an algorithm shows significant translation from where it wants to operate to where it ends up operating under contention. And this is not something that's unique to just these two algorithms. It's true for most algorithms in the Linux kernel that have been deployed on the internet. So we have pulled 4 more algorithms on the internet where all of them make different trade-offs. But when I put them together, again, you get the significant translation from where someone wants to operate to where they end up operating. Now, again, this is not breaking news. We all know this really well. So what am I really giving this presentation for? So the main thing that I want to motivate via these observations is that because these algorithms represent these different trade-offs, a good goal for allowing these algorithms to coexist is not just bandwidth fairness, but maybe trying to minimize this translation between where they operate and where they end up operating when they are competing with each other. So essentially for the internet, I think what we should try to keep as a goal is make sure that competing congestion control algorithms operate closer to the picture on the left rather than the picture on the right, which is what happens in a classic 5-4 queue. More specifically, what we argue for in the paper is that most congestion control algorithms, because they make these trade-offs that exist on the Pareto frontier, what we want to minimize is this movement, and we call this minimization of movement performance isolation, where we say that they're able to meet their performance goals as if they have been isolated by the other flows that they're competing with. Now, the obvious solution for performance isolation, or making sure these flows don't move around, is fair queuing. We can give each of the flows their own queue, and this way they're able to fill the buffer as much as they like, and then everyone's happy, everyone's making the trade-offs that they can make. But often on the internet, you have too many flows and too few queues. So really what this goal dilutes into is how we can provide this performance isolation with just a handful of queues. So if I have tens of thousands of flows, how am I going to isolate them from each other if I just have a handful of queues available in my switch? So in order to make this practical goal for the internet, in our paper, we make two key contributions, or two key observations, actually. The first one is that often you don't need perfect isolation between these flows. You could make do with approximate isolation between these flows. So because a lot of congestion control algorithms exist on this Pareto frontier, you could actually cluster them based on how many queues you have available, and that way you could provide what we call approximate performance isolation between them. So for example, over here, if I've got all of these flows and I've got only 3 queues available to provide some kind of isolation, I could cluster them based on the trade-offs that they want to make, and then assign each cluster its own queue. So that's number one, which is moving from a goal of perfect isolation to approximate performance isolation. But it's still not a solved problem, because we're still left with inferring the trade-offs that a flow might want to make. A packet in a network is just a packet. It does not come with a label saying that, oh, I care about throughput 60% more than I care about delay. So it's impossible for us to map a packet to a specific point in this Pareto frontier or assign a cluster based on just this information. Now, fortunately, we have a technique to deal with this problem as well, and I'm going to try to build the intuition towards a solution step by step. So to start with, let's say somehow my network has converged to a happy place where all of my flows are somehow, in their correct clusters and in their correct queues, and I have a correct assignment. And in this correct stable assignment, I have a new flow that enters, and I'm going to color this flow black because I don't know where it exists on the Pareto frontier. Now, in the state where I have no knowledge about what kind of a trade-off this flow might need to make, I can start by assigning this flow just a random queue. So let's say I put this flow in queue number 2, and then what I can do is I can observe how this new flow interacts with the other flows within queue number 2. So if this new flow turns out to be super aggressive, that's usually a signal that this new flow cares about throughput more than the other flows within queue number 2, which I can use as a signal to promote this flow up to queue number 1, where I'm housing all of my other throughput-hungry flows. And this simple shuffling mechanism can be a really nice natural way to automatically distill the flows within your network according to the throughput delay trade-offs that they want to make. And we can assign them the correct queues over subsequent shuffling rounds. So we built a multi-queue AQM based on this simple intuition, where every round we look at flows in each queue, and all of the nice flows get shuffled down to delay-sensitive queues, while all the naughty flows, they get shuffled up to more throughput-hungry queue. And the reason I'm calling these flows naughty and nice is because we call our system Santa, because every round it's making a list of naughty and nice flows and then shuffling them up and down. So we implemented Santa on a real P4 switch, and in our real implementation, we also made a number of more practical considerations. So for example, the first practical consideration we made was to have a dedicated mice queue where we would house all of our short flows that would be too short to respond to any of these shuffling behaviors. We also gave each queue bandwidth proportional to the number of flows that it housed in order to match flow level fairness as much as possible. But of course, this is a configurable parameter within Santa. We track the throughput shares of each of the flows using the sojourn time of each of the packets, which was then exported up to the control plane, which would use this to make its shuffling decisions, update the bandwidth weights of each of the queues, as well as the initial assignment of flows to particular queues. And I don't need to get into the implementation details, but all of these bits and pieces very naturally fit into the data plane and the control plane pipelines in a P4 switch. So we built Santa over this intuitive idea of shuffling flows according to the trade-offs that they want to make. Now let's see if it actually does meet the goals of approximate performance isolation. So let's just set up, in the paper, we have many experiments where we try to convince the reader that this does indeed happen. I'm going to go over one of these critical experiments in the talk today. More specifically, I'm going to take a very simple scenario where we had 9 long-running flows, 3 each of Cubic, BBR, and Vegas, and we configured Santa to shuffle them every 5 seconds across a system of 3 queues. And to set the context, this is our baseline, which is a simple FIFO baseline, where if we just put all of these 9 flows in a single queue, you can see that Cubic and BBR take most of the bandwidth, at least in this buffer and network setting, while Vegas gets hardly any of the bandwidth. And what we're aiming for is a fair queuing system, where we ran the same experiment, but assigning each flow to its own queue. So what we deal with in most of the internet today is on the left. What we're targeting is the graph on the right. So how did we do? So it turns out Santa does really well over long enough shuffle intervals by isolating flows in the individual queues and clustering them correctly to their correct clusters. And we can sort of observe this in Santa's graph by seeing that there's very little translation from where these flows operated when they were run in isolation or when they were run in fair queuing compared to where and what kind of trade-off they end up making while they're passing through a Santa-like multi-queuing system. In the paper, we compare Santa with many other approximate fair queuing systems that unfortunately are not able to give these approximate performance isolation guarantees. Now, given this performance, I think another natural question that we should discuss before we end today is how many queues is enough for Santa, right? Because we're naturally talking about multiple flows that can organize themselves in multiple clusters. The natural question is how many queues do you need to provide this amount of performance isolation? So we provide analysis for this in the paper as well. And what we show is that Santa actually forms this really neat continuum between a FIFO system that has absolutely no performance isolation compared to a fair queuing system that has perfect performance isolation. So what this means is that if I ran Santa with just one queue, it would run exactly like a FIFO system. But as I start supplying Santa more and more queues, we can see that the operating points of the competing flows sort of start meandering towards their ideal operating points. And indeed, when you supply Santa with enough queues, which is the number of flows, Santa behaves exactly like a fair queuing system over time. In the paper, we have a lot of scalability experiments as well, where we show that these performance isolation guarantees can be met for a lot larger number of flows as well. Naturally, the more number of queues you have, the better performance isolation you can get. But what we have seen with Santa is that at least over long enough time horizons, with just a handful of number of queues, you can often manage to get significant approximate performance isolation. Now, I've presented all the nice results from the paper, but this is probably a good time to point out that Santa is in no way a silver bullet solution for the internet. and I can continue to do congestion control research for many, many more years. And the reason I say this is because, given Santa's simple design, the shuffle frequency is not an easy parameter to tune for a given network. So in the paper, we have mainly looked at long-running flows, but obviously you can imagine this shuffle frequency is going to be a tricky parameter to tune depending on what kind of flow churn you have within your network. We also need to explore more dynamic buffer and bandwidth allocation strategies. So maybe it would make sense to give the throughput-hungry flows more of your shared buffer compared to your delay-sensitive flows, and the same thing goes for bandwidth as well. Finally, this is a new queuing mechanism. It would also make sense to analyze this game theoretically, see if there's a game theoretic way to make sure that there's no way to game the system, or if there is, how can we modify the algorithm to make Santa immune to this? So that's all I have for today. I think the key 3 takeaways that I hope you take from this paper is that bandwidth fairness is probably not the right goal for the internet anymore. Instead, we should look at systems that are looking at things that are similar to approximate performance isolation. And with Santa, we indeed show that this is something that can be practically achieved even at the scale of the internet. Finally, our Santa implementation is open source and available on GitHub. Before I end, this was work that I did with many wonderful collaborators. And please reach out to me if you think Santa makes sense. I would love to hear if it makes sense to deploy within your networks. And more interestingly, I would be very interested to hear where in your network you would think you could deploy Santa. Yep, thank you. And I'll be very happy to take questions.
Hold on. Mike.
Am I up first? Okay, excellent. Thank you. Jana Iyengar, thank you, Ayush, for presenting this. I think this is fantastic work. I read this as basically, we've had FQ in the Linux kernel, for example, but that does require per flow state. Yeah. And I see this as sort of a next level up in terms of congestion points for providing flow isolation where we can't do per flow state. So if that read is right, you're nodding, so I'm assuming that is the correct read of this work broadly.
So the main read is not just per flow state, but also the number of queues that you might have available. Right. Santa does require per flow state because it does still...
Yeah, I get that. The shuffling and everything else will require it, yeah.
But it does apply this to only a subset of the flows. So for example, if the flows are short, you just put them in the mice queue, and that's how we manage state. But if all of your flows need it, it still does not solve the per flow state problem.
But the number of flows that you're showing there are pretty reasonable.
Yeah.
So I would say that this is fantastic because of 2 reasons. One, you're challenging, or you're at least articulating the premise that we've, as a community, known for a long time, that is that flow isolation is something we really, really, really want. And we keep testing things without flow isolation in the network, and you're doomed to failure when you get there. So I appreciate that point. I think that's very, very important. My question is, how far do you need to go beyond this, beyond FQ, beyond Santa, to actually, let me, have you looked at L4S, for example?
Yep.
And do you have any comparisons and analysis of where you might be able to do with approximate isolation versus L4S style, more specific isolation?
So I would imagine L4S would definitely do better, especially in a case where, let's say, Santa also has only 2 queues available to it. The main place where I think Santa differs from L4S is that it does not explicitly require any cooperation from the end host. So in L4S, maybe a client could lie about what its preferences are and then get into the better queue. But with Santa, that's not going to be a problem because I'm going to directly observe what your sending behavior is, and then that's going to translate into what kind of a trade-off I allow you to have.
It's a strong benefit. I hope you point that out on the paper.
Yeah.
Thank you.
Roland Beskaiti. Thanks. This is really interesting. I think one of the key issues is that you have also a queue for mice flows, because short flows would suffer actually from reordering. I didn't read the paper actually, but so how long are the flows that you put into your shuffling queues?
So how we classify mice flows are basically the first flight of packets for any flow. So the first 10 or 20 packets of a flow are always put in the mice queue, which is a strictly high priority queue. And then
okay.
everything upwards from that gets assigned a queue within the Santa queues and gets shuffled around.
Yeah, so I guess let's say the disadvantage of shuffling the packets is probably getting reordering, which maybe may lengthen your flow completion time. But if the flow is quite long running, then that is basically not a problem. So did you look at slowdown metric?
So we did not look at slowdown. Our primary metric was still how much it translated in terms of what the average throughput delay trade-offs were. But we did look at reordering, which was pretty insignificant. In fact, in most of the experiments that we ran, it did not happen. And the reason I think this happened was because we very carefully made decisions on, whether we shuffle the nice flows down first or the naughty flows go up first, and in which order we dequeue from each of these queues. So I think that sort of manages the reordering behavior a bit.
One quick last question. Did you compare it to flow queuing?
I don't believe we did. But I can chat with you offline regarding this. Yeah.
I'm Stuart Cheshire from Apple. I think it's a sign that you're doing good work and giving a good presentation when there are this many people in the queue to make comments and ask questions. So congratulations for that.
I'd very happily take that as well.
Yes, you can benefit from all kinds of feedback. That's true, but it is better if it's delivered politely. So good work, very impressed. I liked your point that you made that too many people assume that throughput is all that matters. So I'm happy to see you making that point. That's absolutely right. In the days of dial-up modems, we all wanted more throughput, but now that you can get 10 gigabit service to your house in some places, it's not all about more throughput. So good point there. One thing you didn't say, but it was, I felt it was kind of implied, not just in your presentation, but in other presentations, it keeps coming up. There's an assumption, an unconscious assumption we fall into that there's an either or choice, that you can have high throughput or you can have low latency and you have to pick one. And the insight of the Kleinrock point is this unconscious assumption we have that there's some linear relationship that as throughput goes up, latency goes up with it, and you have to decide where to be on that spectrum. That's not true. Throughput can go up with the latency being unchanged until you filled the BDP. And then beyond that point, the throughput doesn't go up, but the latency starts going up. So I think there's a really key insight there that you can actually have the best of both worlds. And that sounds too good to be true, which is why people forget that that's possible. So now I'll get to my questions and my suggestions. All of this analysis, and again, this doesn't just apply to your presentation today, there was no mention of ECN, L4S, the Prague congestion controller. And I think in the modern world, that has to be compared. And in some ways, it might be disappointing because if it solves all the problems, then there's less research to be done. But this is not theoretical at this point, right? Your iPhone and your Mac have TCP Prague, and Comcast has deployed L4S marking at the bottleneck. So this is transitioning out of the lab. You said something there about traffic lying to get in the better queue. And I think that's a common misunderstanding about L4S. We've been doing traffic priorities and type of service and traffic classes for 30 years, and it hasn't solved the problem. L4S is not just a new name for the old bad idea that doesn't work. It turns it on the head. L4S is not a better queue. L4S is better information. By marking your traffic ECT1, you're not saying, give me special service. What you're saying is, give me better information about the state of the queue so that I can make more intelligent decisions. So there really is no incentive to cheat with L4S because The win of L4S is using Prague or something like that that makes smarter decisions. If you don't have your sender make smarter decisions, the fact that you promised the network you'd be smart and then you're not smart, you're shooting yourself in the foot. So I guess I've talked enough. We have other people waiting, but overall, good work. Thank you.
Yeah, thank you so much for the feedback. I would probably loop back to the first thing that you said, which is, it's a trade-off between throughput and delay. I agree with that, except I think the trade-off space goes beyond 2 dimensions. So, depending on if you want to optimize for loss, jitter, if you have short flows where you're optimizing for FCTs, then, even though you can make that trade-off, it might make sense to exist somewhere further down the line because it's optimizing some other dimension.
Hi, so I'm Chris Box. I work for BT. Thank you for the presentation. I find it really interesting, and also the slides are nice and clear as well. I appreciate that. So this system is something you're comparing to FQ, and you're saying FQ gives you ideal isolation between flows, and this is a way of doing it with a smaller number of queues. So obviously, I'm just thinking about what does this mean for resource requirements, and clearly you need less memory if you're doing Santa. Have you got any measurements on what it means for CPU? Are you using more CPU because you're doing the shuffling, or are you using less CPU because you have fewer queues to manage? Do you have any numbers?
So we haven't implemented this on the endpoint or on the kernel. We have implemented this in a programmable switch. So over there, of course, the shuffling behavior does take some CPU cycles from the control plane, but these are cycles that are available unless you're running many other algorithms on the switch itself. With regards to your comment on memory, I'm not sure Santa would require less memory. It does require fewer queues, but I think the amount of buffer storage and the memory that you want to use is going to depend more on what your flow churn is, what your BDPs are, rather than a system like Santa. So those are things that I don't think Santa can make up for, but it can allow you to, edge closer towards this goal of isolation while having fewer queues.
Okay. Yep. Yeah, makes sense, because my mental model is just like a Linux kernel being a router, and so everything's running in the kernel in doing with normal CPU. So I get, and I clearly understand that with different hardware that trade-off is different. But, all right, thank you.
Thank you.
Hi, Danish from MPI. I have a few questions, but I will start with the simplest one. Have you tried this in the multiple bottleneck? Because in the first bottleneck, you are already touching the dynamics of the flow. So in the second bottleneck, it might get impacted. I mean, the objective of the flow is changing. How do you set the objective for the next one?
Yeah, that's a great question. That's not something that we have looked into in a lot more detail. I think it's going to be very interesting to see, because depending on which queue your flow gets shuffled into, you can potentially have moving bottlenecks where you get shuffled into a queue where this is no more the bottleneck anymore. Now your bottleneck moves somewhere else. So you could have shuffling bottlenecks within your network as well. So I think it's a great question. It's a very interesting dimension, but we haven't investigated this yet. This is something we're still looking into.
Okay, I have one more. About the flows with different RTTs, because RTT is changing the objective. I mean, objectives are the same, but the RTT might make a flow more throughput hungry than the other one, right? Then how do you set the fair queuing for these?
So I think that's the beauty of Santa, which is that it does not care about what your RTT is or it's going to purely behave based on what your sending behavior is. So even if I had all 9 flows being cubic, for example, and they had different RTTs, they would be shuffled across according to the aggression that's a function of the RTT rather than the algorithm. So yeah, to answer your question, it could still help with RTT unfairness as well. And it does not explicitly try to do this. It's just the natural shuffling behavior achieves this.
Thank you. Nice talk.
Thank you.
Mike. Hi, I'm Gary Fairhurst. First of all, thanks for bringing this here. And I was going to ask about RTT unfairness, but you've talked about that. I'd encourage you to perhaps look at more queues than just one or two, but probably a handful is probably enough. And I think for me, that's the beauty of what you presented, the simplicity. Yep. So I'd love to see a comparison sometime. Maybe you've already have thoughts against L4S in terms of the complexity of actually implementing this. Have you thought about that yet?
So we did look at, so it's not a very complex multi-queue AKM to implement. And we sort of try to demonstrate this with the practical implementation that we have in P4. But of course, we have not compared this with L4S. So that's something we would have to look into.
Okay. And finally, when we wrote RFC 9743, which you may have come across or not, we talked about harm, and rather than taking bandwidth or some other metric, but look at how much you harm other flows. And I think I understand that's kind of what you're looking at, the impact on the other flows rather than the benefit of that particular flow.
Yes. So I think there are multiple ways to approach the issue of harm. If you just look at the shuffling behavior, it's trying to minimize the bandwidth harm that it's doing. But from a more theoretical standpoint, if you isolate flows, then it makes them impossible to inflict harm. So that's also one way to minimize harm, which is if you know flows have shared goals, then you can club them together, and that should also, in theory, minimize overall harm, whatever your harm metric might be.
Thanks for your talk.
Thank you.
Mohit, hi Ayush, thanks for bringing this here. I have one question and one comment. The question is, I was just looking at the paper. Have we tested with 90 flows maximum, or is it any number beyond 90 that we have tested?
We have only tested with 90.
With 90 flows.
Yeah.
Okay.
Yeah. But these are like real flows from the Linux kernel.
Yeah, I saw 30 cubic, 30
Yeah.
PBR, 30 Vegas across 3 queues and then 6 queues. I was just looking at it. Thanks. Okay. The comment is about the word FQ. So I think we are, I see it's mainly referred as fair queue.
Yeah.
There's also flow queue, which is slightly different. And there was a little bit of similarity that I find, and maybe it will be very interesting to see if we could see how Santa can further be combined with flow queue also, because flow queue has a property of maintaining 2 different sets of queues. Of course, there are many different queues, but 2 sets of queues. One is new flows and one is the old flows. Beyond that, it has something called sparse flow prioritization. So your mice flows automatically get higher priority during the DQ using a slightly modified version of DRR. And I believe that we may be able to reduce the shuffling by a lot if you try to incorporate and see if it is a flow queue. A flow queue naturally does this property of, it has a property of prioritizing the sparse flows of the mice.
Yeah, so I think we came across many similar ideas in other data center flow management systems as well, where you treat the first few packets. I mean, obviously you don't know how long a flow is, so each new flow sort of gets treated as a mice flow and it gets its own mice queue. And that is something that we try to implement in Santa as well. So Santa also has a single dedicated mice queue where the first 10 packets of each flow are shuffled with high priority.
With flow queue, you will have several queues for mice flows, not just one queue. And then again, there's a further priority on that. So maybe it will be just interesting to see if Santa can be tried upon that.
Definitely. Yeah.
All right, thanks.
Hello. I want to say almost exactly the same thing as Mohit, maybe with a little less knowledge about the same thing that he's talking about. So the primary thing for me to say is that I'm excited about it. I think this is really, really good work. That other thing, so maybe I'm misrepresenting the flow queuing behavior. My theory has been, not knowing the dynamics exactly, that a new flow in that system that is prioritizing new flows may be a flow that just doesn't have anything in queued. So I think we may have a case where there is a flow that just doesn't have a queue, and you get a new packet from that flow. You basically treat it almost instantly, and it goes away and there is no queue, right? Whereas in your system, if I'm imagining a flow that, you know, a sparse flow like a voice over IP flow or a gaming flow or anything that isn't really queue building, it might end up being queued together in, you know, with flows that do have a queue, right?
So we do have a timeout on how long a flow must be active. So what we do is we have like we have a table where we index each of the 4 tuples that we've seen in the past fixed horizon. And within this fixed time horizon, if you send less than 10 packets, you're always going to be within the mice queue. If you send more than 10 packets, then you're going to be promoted within the Santa queues. But I mean, it is a very important aspect that you pointed out at, you know, tuning these parameters is going to make a massive difference in terms of, you know, how many things end up in the mice queue, how many things end up and how often you shuffle them as well. So yeah, I completely agree. These are parameters that we don't currently have a good strategy for tuning, but this is something that we would have to look at.
I also think like there will be ways to tune that more and more and more,
Yeah.
but I think this is the absolutely right direction to go. So this is really great.
Yeah, thank you.
Thank you. Just on the FQ question, when I mentioned FQ on the Linux kernel, I did mean
flow queue.
Flow queue.
Okay.
Bob Briscoe's not here in person, but his spirit hangs around in these hallways, so I'll invoke it. Have you looked at how applications, so application utility tends to be application utility. Flow is thing that we like to engage with, but applications don't care. And in an FQ system, typically you will have this problem that gaming can be gamed.
Yep.
Have you thought about it? Have you done any simulations to figure out how that performs with multiple? You get multiple bandwidth shares is really what I'm asking for.
We haven't looked into it yet. Yeah.
I would say that's an important thing to consider.
Yeah.
You mentioned that you had to do some game theoretic analysis. This is actually fairly simple in terms of just doing a simulation and seeing what actually happens.
Yeah. We would still have to. Yeah, I would still have to look into it. I don't have a good answer for you right now. So I agree. Flow level fairness has the
no meaning.
Yeah, it has no meaning.
That's the phrase you're looking for. Thank you.
Thank you.
Cool. I think that's it for today. Thanks for being with us for 2 hours. And yeah, see you next time.